Hello, everyone. Thanks for being here today. I'm going to talk about something we've been working on, a way to bridge the validation gap between design and engineering. And we did it using a tool many of you might already know, Dynamo Player. Before we get into it, let me briefly introduce myself. My name is Chaeong Kim, and I've been with Hyundai for over 8 years. Our team manages design data from the early concept phase all the way through to production. And we are divided into two groups, one handling exterior and the other interior. I am part of the exterior group. I spent my first 6 years focused on cost modeling, and now I'm continuing to expand my role into CAD-based surface development as well. I should also mention my colleague, Young-bok. He's here with us today and actually led this research from the start. So if you catch him later, he probably has all the real answers. Here's what we'll go over today. First, the gap. I will look at some common issues we've seen during the design phase. Second, the solution. I'll show how we turned some critical requirements into lightweight validation tools using Dynamo. And finally, what's next, where we are planning to take this approach moving forward. All of this centers around one goal, making design validation in Alias faster, simpler, more reliable. Let's start with this. I searched for architecture expectations versus reality. And these are some of the results. On the left, a beautiful rendering. On the right, the actual building. Same story here. And here's one more thing. Pretty different, right? And as you know, it's not just architecture. We've all seen this in car design too. Even when a design is created with production in mind, there's often a big difference between early concepts and final models. And it's not just due to the design revisions. So what's really causing this? The obvious answer is requirements. Things like regulations, structural constraints, and manufacturing limits. And among them, it's especially important that key requirements affecting the design are applied at the right stage of the process. But we've found there's something else at play. One of the bigger issues we've noticed is that the same requirement can be seen very differently. The engineer may think in numbers and formulas. The designer thinks in shapes and lines. That gap in understanding leads to changes that technically pass, but don't match the original design intent. To move forward, we need more than just a list of numbers. We need a shared understanding of why the requirements exist and how to meet it without losing the design vision. This is where our role comes in. Instead of waiting for engineering reviews, we thought, why not check these things ourselves? Because we talk to designers every day, we understand their intent. And since we build the data ourselves, we are in the best position to validate these requirements in real time. So that's what led us to start building our own validation tools right inside the Alias using Dynamo. These tools help us catch problems early, avoid unnecessary back and forth, and stay true to the design from the start. Just to give a bit of background, tools like CATIA often come with built-in validation features, and some companies even customize them further. Alias, on the other hand, is without question the best tool for automotive design, especially when it comes to surfacing. But when it comes to applying production-level checks directly inside the Alias, we found some limitations. That's where Dynamo came in. Since it's already built into Alias, we used its flexibility to create our own validation tools, simple, practical, and tailored to our workflow. It wasn't originally meant for validation, but that flexibility is exactly what made it work for us. We used it to build simple checks customized to the real-world requirements we deal with every day, and easy to run while modeling, not after. Before we get into the actual tools, let me quickly walk you through the 3 checks we focused on and why they matter from a design perspective. First, stiffness conditions. This one affects how curved surfaces like the hood or roof can be. To meet stiffness targets, sometimes we have to round things out more than we'd like, which can go against the sharper or flatter designs we are aiming for. Second, the corner gauge check. This is part of a regulation for pedestrian protection. It often forces changes to the top curve of the front bumper, especially if it's not considered early on. And those changes, they can be quite visible. And third, external projection. This one's about the rounding of sharp exterior edges. Even though the change might be small, like softening a grill lip, it still impacts the overall feel of the design. The key is when we validate. If these checks are only done at the very end, we often run into rework. And worse, we risk losing the original intent of the design. That's why we focus on validating certain requirements earlier in the process, right when we are actually building the surfaces. Let's start with the stiffness. Flatter surfaces may look clean and bold, but they are harder to stiffen. And depending on the material and thickness, the required values can change a lot. Here's a quick example. If you try to build a Cybertruck with conventional sheet metal, well, this is probably what you end up with. Not quite the bold, futuristic look we are going for, right? So how do we check stiffness in Alias? It starts with a few reference points on the hood. 500L, the cowl point, and the zero line. We plug those into a stiffness formula that gives us a value based on curvature and geometry. It's the same for the roof, with slight variations depending on the roof type. Honestly, the math behind it, I just want to avoid explaining it. But that's the point. Once it's built into Dynamo Player, the check itself is quick and simple. Let's take a look. In this case, the required value was over 8.0. Even after setting the sheet metal thickness as requested by engineering, the result didn't meet the requirement. So we had to add volume to the roof surface. We adjusted the shape just slightly, enough to stay within the allowable range from the design team. Then, using our tool, we rechecked it in real time and it passed. The final result exceeded the required value. And since each company uses different materials and manufacturing methods, the stiffness value can act as a reference, not a fixed rule, but a helpful guide. Next, let's talk about the corner gauge check. This one comes from pedestrian protection regulations, specifically from UNECE. And for global manufacturers, this isn't optional, it's mandatory. The rule defines the corner of the front bumper using a 236 by 236 millimeter scale plan, tilted at 60 degrees. You move this plan around within 42 millimeters of the back beam to find the first point where it hits the bumper. If it doesn't hit where it should, you've got a problem. Let me show you a real example. This is from the early design phase of GV60, one of our production models. When we checked it against the regulation, we realized the contact point wasn't within the allowed zone. You can see how the bumper design eventually changed here in the final version. Now, the regulation wasn't the only reason. The shape also evolved through the usual design refinement process. What made it difficult, though, was how many times we had to go back and forth, adjust the surface, check the corner gauge, tweak the design, and check again. It was hard to keep track, especially as the design kept evolving. If we'd had a real-time way to check the contact point during the modeling process, we could have saved a lot of time. So here's what we did. This video shows how the Dynamo tool creates a 60-degree plan to measure the bumper corner and uses it to find the nearest contact point on the bumper surfaces. Actually, creating and tilting a plan by 60 degrees is pretty easy to do in Alias. But identifying the exact contact point manually took time, and it was easy to make mistakes. Especially when the surfaces were adjusted, it was impossible to see the point update in real time. Now, we've automated the entire process using Dynamo. Just pick the bumper surfaces, run the script, and it shows the contact area right away. So now, let me show you how we actually use the tool in a real workflow. In this case, the goal was to bring the corner gauge contact point inside the 650L line. With the validation tool, we could easily check the coordinates of the contact point and adjust the surfaces in real time, seeing instantly how those changes affected the result. As you'll see in this clip, we are now able to check the corner gauge zone directly as we model, which helps us stay aligned with the requirement from the very beginning. So we are not stuck fixing things later after we've already fallen in love with the shape. And lastly, let's go over external projection. This check also comes from UNECE pedestrian safety rules. And it's all about protecting pedestrians from sharp edges. The logic is pretty simple. Use a 100 millimeter sphere to test surface gaps. If the distance between two contact points on the sphere is more than 40 millimeter, then you must apply at least a 2.5 millimeter radius to the edge. Now, this doesn't always change the whole design. but it can impact sharp details like grill edges or surface breaks. And sometimes those small details are exactly what give the design its character. Here's an example. This is the same grill, but with a 2.5R applied on the right. If you are aiming for a sharp, refined look, that 2.5R might feel a bit too much. So how did we build this into Dynamo? We offset the surfaces by 50 millimeter, found the intersection line, and placed a series of virtual 100 millimeter circles along it. If any of those circles touch both surfaces, we mark the point as a COS, meaning the sphere has touched both surfaces. Since the COS points update in real time, we can adjust the surface and see immediately whether your changes meet the rule or not. In one project, the gap between the grille and the bumper was too wide. Engineering suggested two fixes. Either add a 2.5 radius to the grille lip, or push the lower lip forward. But both of those options had downsides. One dulled the edge, the other broke the line at 0L. So instead, we used the Dynamo tool to find the third option, adjusting the curvature of the lower bumper surface to close the gap just enough. Let's keep watching from here. It worked. We passed the regulation and kept the grille lip as it was. Until now, to check whether our design met the requirements, including external projection, we always had to request the reviews from the engineering team. That meant converting the data, submitting it for review, waiting for feedback, making changes, and repeating the process again. Sometimes it took a day. Other times, nearly a full week. But by using these validation tools, we can not only preserve the design intent from the styling perspective, but also significantly reduce validation time and minimize unnecessary revisions. That's the real value here. So where do you go from here? We are continuing to improve the tools we've already built, but we are also expanding into new areas. Some of the things we are looking into are grille cooling checks, lamp visibility, and glass curvature. Among these, grille cooling is a big one because it often influences the front-end design. In some cases, the grille lip had to be slimmed down, or the unit layout had to be adjusted just to increase the cooling area. Right now, if we want to check the cooling area in Alias, we use the mass evaluation tool. But before that, we have to manually subtract the grille surface and any internal structures inside the zone. It works, but it's time-consuming, and it breaks the flow. So we are working on a Dynamo script that automates this whole process. The idea is simple. You select the design surface, the grille area, and the cooling boundary, and it gives you the effective cooling area in one step. We are also planning to get support from Autodesk Consulting to refine the logic and make it run even smoother. It's still a work in progress, but we are excited about where it's going. That wraps up everything I wanted to share with you today. At the end of the day, I believe our role shines most when you move beyond just building data, when we actively help to improve design. Because in the end, we are all here for the same reason, to create good designs. Thank you.